So now that we kind of get the idea of the relative size of a p-value and what it implies, we're going to begin this journey of hypothesis testing. And the idea of a hypothesis test is to go backwards from the results that you just saw in the previous bit and reverse engineer the way to take the data and, actually not reverse engineer, forward engineer, turn the data into something that generates a p-value. That's kind of the point. We're going to take the data and generate a p-value from that said data. So what we're going to look at are the different methods of it. And we're going to start today by looking at testing a single parameter. Now we've looked at two parameters already in this class in the form of confidence intervals. What are the two parameters that we have looked at so far in this class? The two parameters that we were interested in studying but can only do so through samples and then forming confidence intervals around our sample centers. Give me one of those two parameters we cared about. Good, mu, the population average. Very nice. Average circulation, average weight, average height, average range of motion. Lots of averages, good. And the other? Be brave. Little p, little p. We're going to start with that one today. What we're basically going to see is we're going to see a corollary. So the single parameter is going to go one of two ways. It's going to go little p and mu. We'll deal with mu starting on Thursday. I want to do one at a time. And what we'll eventually do is we'll broaden this out into other kinds of tests. Testing 2 means and 2 p's, and testing 3 or more means and 3 or more p's. But right now, first things first. Single proportion testing. Single proportion testing. So this is the formal title. We're going to be hypothesis testing. Oh, camera back here. Hypothesis testing a claim. A claim. This is Ashley's alternative hypothesis she was mentioning earlier on a population proportion. And what I've tried to do is break it down into a 4-step plan. There's a nice 4-step plan, 2 of which you're already familiar with. Not 1 and 2, but 3 and 4. After the last homework set, you guys have already been interpreting p-values and stating conclusions, or at least reading conclusions. What I want to do today is I want to get into some real data and start extracting the results from that real data. So the first question I have is the flu vaccine working that we're studying? So you look at your data sheet there and you notice that there's a flu rate that's 12%. So in the general population, there's a certain flu, it hits at 12%. All right? You or somebody is creating a new vaccine to try to fight this flu rate, and they give it to 1,000 people. 1,000 people got the vaccine, 101 got the flu. What do you think? Is the vaccine working? Ken?
I say no, because the reason why is it overlaps. When I put the figures in at 95% confidence,
Love this.
it overlaps.
So what we're saying is we've got overlap on the interval, and I don't see yet. Can we create an interval for this? What do you think? Can we use old techniques? Yes, for sure. Let's create some old techniques. All right? Great. So, we have a belief that this flu vaccine is, well, we don't believe in anything. We want to see if the flu vaccine is actually working. So what should we run, do you think? As far as a tool, what should we run right now to see if the flu vaccine is working?
One prop z.
One prop z int. Stat tests. One prop z int. Yes. Oh, goodness, that is super. Thank you, Michael. There we go. So I got bumped in the bag. That's visible. Yeah, that's good. All right, so one prop z int. What goes where? Say that again. X is 101 because 101 people got sick out of the 1,000 that we gave the vaccine to. I think 95% confidence is good. Let's calculate that bad boy. All right. So, what we have here, I'll draw a quick little image to go with it. We've got flu rates in the general population. along this axis. And because the flu rate is at 12% and the vaccine ostensibly is lowering it, I'm going to put 12 over here on this side. The lowest that gets is about 8, so I'll put 8 over here on this side. So we got 9, 10, and 11. Okay. Now all we were told is that the vaccine is trying to lower flu rates, and the flu rate is at 12%. Based on this confidence interval, does it appear to be working?
No.
No,
Why?
because it's fitting anywhere in between the ranges that we have.
So that range right there,
It doesn't exceed the 12%, but it's not far enough down.
careful,
But-
we're not going for practical, just statistical significance. So is that interval significantly different than
No.
12%?
Yeah.
It
No.
depends on how you round it, but it is it not?
No, because-
That's very close to 12%.
Because you have to run the 12% through the one prop z anyways.
That's a parameter,
But
Right.
the margin of
not a
error.
statistic.
But if it
doesn't get a margin of error.
It doesn't?
No, that's a parameter value. This is important. Jared, thank you for this, by the way. This is awesome. That 12% doesn't get a margin of error because it's a parameter value. It's being reported to you. They didn't say we drew a sample of people and 12% of them in the general population got the flu. They said the flu rate is 12% in the general population. That's a parameter value. That means if there is a margin of error, it's infinitely skinny because it's been documented for so many years and so many years and so many years that there is no plus or minus on it. You're absolutely correct, Ken, what you said originally. If it had a margin of error, a plus or minus, but it doesn't. It comes at you as a parameter value. So essentially, what you're seeing here is you got an 8.2% here, up to just about 12, but just a smidge below. So this is the flu rate with the vaccine. And that purple line is the flu rate without the vaccine. Now I know they're very, very close, but they're not touching, which means the interval shows significance, if you will. It shows significance, if you will. I'm not talking about practical significance, but you can say that there is a teeny difference at the max, and maybe a sizable percentage point difference over here. So you can say that using a confidence interval. However, what I want to do is I want to show you an extension of the confidence intervals that these hypothesis tests are all about. If it were up to me, it's not, just so you know, but if it were up to me, I would run everything with confidence intervals. And I would teach you guys how to do one-sided as well as two-sided ones. The reason I don't like a two-sided interval in this one is, what are we trying to show a vaccine does? What are we trying to show? If a flu vaccine is working?
It's preventing.
Yeah.
Say that again.
It's preventing the flu.
Define preventing. I love this, Michael. Define preventing.
It's preventing the effect of the flu essentially 95% of the time.
So I want to define preventing again too. As far as the effect, if the flu rate's 12% in the general population, what should the flu rate be for those who take the vaccine? It should be down, correct? It should be down significantly from 12%. In other words, it should stop us from getting the flu in the first place.
Well, essentially, that should be 95% on the other end, correct? No.
Good, yes.
Okay.
That's the catch. The catch is, I don't want a two-sided interval. What I want to see is, I want to see a one-sided interval that has a max value and says it can't go any higher than this. And I want that max value to be less than 12%. Does that make sense? So I don't want it to stop at 8%. I want it to go essentially down to 0. But I want it to go up to say that if you take this flu vaccine, I'm 95% confident that I will not get the flu at a rate higher than, say, 10.5% or 11%. I don't want it to cap off down here. So I have to do this thing called shifting the 95%. We saw it last week. We saw it last week with green tea and breast cancer. We saw it with caffeine and heart rate raising and lowering. We saw it with secondhand smoke and lung function. All those intervals last week were one-sided. Do you remember? The 95% area was all on one side or the other of the curve. It wasn't trapped in the middle like this. Essentially, what you're looking at right here, what you're looking at is you're looking at a bell curve like that. So you're seeing two standard deviations around that bell curve. That's what a 95% confidence interval is. I know it hides that when you hit one prop z in and you see that. But there is a bell curve around that traps two standard deviations. I want the 95% with those two standard deviations shoved this way. because that's going to give me a better picture of the reduction, not the potential increase, but only the reduction using the flu vaccine. I know that seems a little bit weird, but that's the whole point of hypothesis testing, is to give us, if you will, this one-sided confidence interval. Cool? It might seem a little weird right now. That might be like, okay, I'm gonna trust you because you haven't led me wrong yet. But that's the point of it, is it allows us to set up any number of sides we want, 1 or 2, in a very effective way. And for some reason, and I don't have a good answer for this, one-sided confidence intervals are not in any textbooks anywhere. They should be. They should be. But they're kind of masquerading, if you will, as these things called single proportion hypothesis tests. So anyway, let's shut the TI down for a moment. Although we're gonna use him quite often once we get going. And let's fire back up this, the first of 4 steps of our plan. The first step is we're going to define the variable. Now we know what the variable is already, but we're going to define what the variable stands for, which is something that most textbooks do a pretty crappy job at doing, is actually defining this variable. So step 1 is to define that variable. I'm going to slide this camera over to the other side over there. We're going to use this board to kind of, we're going to start this variable up. All right, we'll come back to that image later. I'm just going to put step 4 way over here. It's okay with you guys for now. That's going to be step 4. We'll get to that eventually. So I'll put it over here so we can jump right to it when the time comes. We'll come back. Because that's what we're going to do. We're trying to decide if we believe the vaccine is actually working to lower these flu rates. So that's going to be our conclusion at the end. Okay, so step 1. Step 1. Let's define that variable. What was the variable we're testing again, friends? Remind me. Say that again. And how are we going to measure that? If we see in flu rate. Boom. Rate, proportion, percentage. So our variable is going to be little p. Little p. Not big P. Damn it. Sorry. Little p. Remember, there's a big P that's the p value, and little p is a percentage. There's also p hat. We'll deal with all this momentarily. We'll deal with all this. I know. So little p. What is little p going to be? What is that? The flu rate of? This is going to be the flu rate of those, say that again nice and loud, that took the flu shot, that had the vaccine bet. Flu rate of those on the vaccine. Flu rate of those on the vaccine. Flu rate of those on the vaccine. Do we know what that is right now?
No.
No, we don't. We do know some flu rate, right? What's the flu rate we know? 12%. That's the flu rate
Of the population.
of the general population. We are going to try. I'm going to go ahead and slap the symbols for H. Not. Do you guys like H1 or HA better for the alternative?
1.
H1? Okay. You can put A if you want. That's totally fine. I heard 1 vote for 1, so we're going to use that. Both of these hypotheses you can write in words. So what do you think in words? I won't write these out. I won't write these out because we're not going to need to write them out because we have the variable defined now. What do you think H1 is going to say? Based on all our discussions from last week, what do you think H1 is going to say? Karen, go ahead.
I think it's going to say that those that took the vaccine still got the flu.
At what rate?
We don't know. That's
Correct,
the
but if the
beta.
vaccine's working, it's going to be
Less than 12%.
less than 12%. That's exactly what goes in H1. H1 is the breaking of the status quo. The status quo is that the vaccine's not working. Remember, if we're trying to show the vaccine is working, we have to prove that it's not working. It seems strange, but this is the whole idea of a proof by contradiction. So, we're going to try to show that it's working. Now, it's working is what goes in H1. So, the proportion of those taking the vaccine are going to get the flu at what rate?
Less than 12%.
Perfect. Less than 12%. Does it say how much less than 12%? No. So the only implication with that less than sign is there's a word that goes between the variable and that less than sign. And what is that word we keep repeating over and over in this class?
On average.
Oh, good. Oh, sorry. Yes, good. On average, the people that take the vaccine are going to get a flu rate.
Less than.
What word right before less than that we don't always say, but is always implied?
Equal.
Oh, no. Statistically,
Significant.
significantly less. I'm sorry. That was probably a terrible question. I was trying to say, I don't know how much less. I don't know if it's 11%, 10%, 9%. All I know is we're setting up an interval that's not going to touch the 12%, which means it's statistically significant. Is that fair? You see what I'm getting at there, friends? All we know is it's not going to touch the 12%, which makes it statistically significantly less than 12%. Believable-ish? Okay, we'll come back to that. What goes up here? And you guys are already on this based on your response from last time. Greater than or? Good. Greater than or equal to 12%. Because if the vaccine's not working, one of two things is going to happen to those who use it. They're either going to have the exact same flu rate as the general population, or they might even increase. That would be kind of a bad thing, right? You give people flu, so all of a sudden they come back with a 36% infection rate. Okay, let's try again. Right? So these are going to be your hypotheses. Now, what's cool about this is you can actually, with this definition of the variable up here, you can read what they both say. We're trying to show that the flu rate of those who took the vaccine is significantly less than 12%. That's the point of our test, to see if we can believe this. The opposite of that is that the flu rate of those who took the vaccine has exceeded or is equal to 12% still. So essentially, H naught means nothing's changed. If you will, this is the status quo. If you will. No effects did. I thought you might too. So yeah, it says basically nothing's changed. Or at least your vaccine's not working. So nothing's changed. We can't reject that belief. Somebody used the word reject before. It was awesome, by the way. Fair enough? One little aside here, and this is something that's happened in the past like 10 or 15 years. Very often nowadays, this null hypothesis, they just put an equal sign up there. Not the greater than and equals or less than, they just put an equal sign up there. I'm not entirely sure that I don't like that. I'm not entirely sure. I don't like that. I like it being exactly the opposite of what's in the research hypothesis. You can put anything you want. I'm not exactly sure what your book does. You put either. I think it's easier mathematically to do what H1 is, and then H naught is whatever the opposite is. So if it's less than, the top's going to be greater than or equal to. If the bottom's greater than, the top's going to be less than or equal to, and so forth and so on. You put either. I just want to give you a heads up that it seems like industry nowadays, this is kind of the favored way. I like this. I like these being exactly the opposite of each other. So your call. Just be aware of that, I guess, is what I'm saying here. Just be aware of that. Fair enough? Good? All right. Step 1.5. I want to make a nod to it here. Step 1.5, go get your data. I call this step 1.5. It actually could even be step 0.5. It could happen before your hypotheses. How could your data happen before your hypotheses?
Because
Say that, Michael?
you need some data in order to form the hypothesis.
Sure. What if you even know, what if we're talking about a flu vaccine is entirely developed to try to reduce flu rates? But suppose you're studying something else. Like you want to see if there is some kind of effect of, say, more sunlight on pilot view. This is one that HDFS folks do, not HDFS, natural resource folks have done. They look at north and south sides of pilot view and look at erosion and veg cover on both sides, vegetation cover on both sides. You might not know what the effect is until you get your data. So you may have to get your data before you form your hypotheses, or you may have hypotheses that you want to test, you have to go get your data. Either way, in this class, most of the data has just been handed to you. Yay, for us. And the other data that's not will be collecting in class together. So I put that as a step 1.5. Just be aware that you'll have entire classes devoted to that step eventually. Okay, good. 2, take the entire data set and put it into the statistical sausage grinder that is a test statistic. Let's talk about this bad boy. I'm going to go here with it, I guess. Step 2. Okay. Now I want you to think back. I want you to think back to single proportion confidence intervals. What was the name of that bad boy? Single proportion confidence intervals in your TI. Remember the name of that little guy in your TI? Oh, good, good. He's basically the same thing as that. I heard Stanormal, which was the little program I gave you. What was it called, Stanormal?
Normal distribution.
Because it was on a normal distribution. And what letter do we use to stand for the normal distribution? As far as the variables on the horizontal axis? Be brave. You got to marry, it's Z. The test statistic for proportions is also a Z-score. And if it's a Z-score, that means essentially it's what? It's a blank of blank blanks from blank. Or a blank of blank blanks away from blank. Somebody just said it. It's a number of standard deviations away from... Boom! That's what it is. What you're going to do, essentially, what the test statistic is, you're going to turn that data that's on your sheet into a number of standard deviations away from average. Why would you do that, do you think? Why would you do that? To see if it's a typical result. Thank you, Ashley. To see if the result you've got follows the curve that's described here, or follows maybe a different curve that is indicated by this one. There's only one curve we're going to draw on the board. It's the one that's centered on 12%. We're going to draw it here in a minute. But first, I want to get the Z-score. I want to get the Z-score that goes along, and then we're going to see where that thing falls. Okay? So we're going to start with a Z-test statistic. Every test statistic is formulated essentially the same way. You know what? Time out, time out. Let's do a generalization first, okay, before we go to specific. Let's do test statistic. This is going to hold for the whole course. So let's get a generalization on the board, and then we'll break it down to specificity as far as this particular test. Any test statistic is formed just like the Z-score was formed back in 243. Remember how you form a Z-score? Something minus something over something. Remember what the somethings were?
The average.
Good. Average in the sample. So what are you thinking? I love that, Mary. Thank you. You got it. What are you thinking? Tell me. Tell me. You got it. Tell me. Whatever's on your mind. You sure?
Yeah.
I don't think so. So I heard average in the sample. And the difference between the average and the sample, say that again, and the assumed average in your, wait, the population? I heard it over there. The assumed average in the population divided by, yeah, you got it. So basically you're looking for the difference between the average in your data and the average in your population, and you're normalizing that with your standard deviation. So here's what it's going to look like in general. You're going to have your samples center. We'll get to him in a second. And don't be like, oh my God, I can't remember that from 243. It was like 6.5 weeks ago. Totally fine if you don't. There's a reason we're going over it again. So don't get panicked. It's your sample center minus your assumed null hypothesis center. And that's great, except it's not good enough. You're going to divide that by the standard error of the samples. Once again, our friend standard error comes back to say hello. Hello. This is the way every test statistic is going to look. You're going to take your data's center, whatever it is. That is going to form the center of your sampling distribution. You're going to take the distance between that and the population's average, assumed from the null hypothesis, and that's going to give you a percentage distance, which is great, but the problem is standard deviations don't have a percentage difference. So you have to divide that shebang by the standard error, which removes the units and puts it back to actually standard deviations. Let's come over to this front board here, friends. We're going to need some more space to do this. Okay, this is the one and only time we'll do this manually through Z-tests. There's no need to do it manually after this. Once you see how it works, you're like, okay, I remember this. Okay, let's get these out. We'll put a new curve up in a minute. All right, so step 2 continued. So the test statistic in our case is going to be called Z, because we're going to be comparing it to a Z distribution. So what we have to do is, we have to get our samples center. Remember what that guy's called? He's once again a little p, but it's p hat. This is little p hat. minus the assumed population center. And that's going to be little p. So now, make sure you see the difference between these two things. That one's got a hat and that one doesn't. Is that important? That one's got a hat, that one doesn't? P hat? I'm sorry. I think so. Was I being PG inadvertently?
No.
Okay, that one's got a hat. Oh, I see. Got it. What's the difference? Say it again.
Sample population.
Everybody.
Sample population.
Sample population.
Okay, that's the difference. You're trying to see if there is a difference. If they're the same, what is that value going to be? If they're equal to each other,
Zero.
it's going to be 0. They are never equal to each other. It just doesn't work out that way. But the question is, are they different enough to be statistically significantly different? And that's what we're going to find out. But this won't do it by itself. This will be a percentage difference. Let's go one more step. There's a fraction for this. But let's just throw the values in for this right now. What's p hat in your sample? What's p hat in your sample?
It was 10.10.
Wasn't it?
1.
It was 10.1%, correct? It was 101 out of 1,000. It was 101 out of